So today I'm going to talk about inner product spaces, which is in the text, chapter 5. And we have that V be a vector space over the field R of real numbers. And a linear transformation is a function from one vector space to another. In particular, R is a vector space over itself. So a linear transformation phi from V into R is called a linear form, or a linear functional. So both terms are used, and if you see them, you know what they are. So every vector, phi assigns a real number. And because this is a linear transformation, we know that the following two properties are satisfied. Phi of v plus w is phi of v plus phi of w for all vectors v and w in the vector space V, and phi of any scalar times v is c times phi of v for all vectors v and v and all scalars c in the reals. So that's a linear form or a linear functional. Sometimes we have the following generalization of this. Suppose that v and w are two vector spaces over R. They could be the same, they could be different. A function f from v cross w into R. I'll explain again what this product of vector spaces is a function such that the following two properties hold. Well, maybe let me just say what is v cross w. So v is a vector space, w is a vector space. V cross w is the set of all ordered pairs of vectors v comma w, where v is in v and w is in w. And we define addition of pairs coordinate-wise. And we define scalar multiplication of a pair also coordinate-wise. And with this definition of addition and scalar multiplication of pairs of vectors, we get a new vector space. So v and w are vector spaces. So is v cross w. And a function from v cross w into R, so a function v cross wr is called a bilinear form, or bilinear functional if it satisfies the following two properties. You take f of v plus v prime comma w, that's f of vw plus f of v prime w. And f of a constant times vw is the constant times f of vw. And the same properties hold with respect to the second coordinate. F of vw plus w prime is f of vw plus f of vw prime. And f of v constant times w is the constant scalar c times f of VW. So a function from a product of vector spaces to the reals is called a bilinear form or bilinear functional if it satisfies these four conditions. Now, if you took Calc 3, you've already seen this, but I'll show you the basic example in a moment. We say that a bilinear form, F from a vector space times itself to the R is called symmetric if f of VW equals f of WV. You can reverse the order of the variables for all vectors V and W in your vector space. And that's a symmetric bilinear form. A bilinear form is positive definite if f of V comma V, you apply the form to the pair V, V is positive for all vectors V and V not equal to 0. So here is the fundamental example. Suppose we take V to be Rn, and we look at, and we take two vectors, let's say V is x1 to xn, and Y and W is y1 to yn. So V has coordinates x1 up to xn, W has coordinates y1 down to y sub n. And we define f of the vector VW to be the product of the coordinates summed. So you have x1, y1 plus x2, y2 plus xn, y sub n. And this is a real number. Because the x's and the y's, these coordinates are real numbers. And if you took Math 226, vector calculus, this f of uv, or f of vw, is just what was called the dot product in Calc 3, vector calculus. And this is a generalization of this to n dimensions. So why is this a bilinear form? Why is it symmetric? Why is it positive definite? So if we take, let me just check one or two of the properties. So this is V. Suppose V prime is x1 prime down to xn prime. So V plus V prime has coordinates x1 plus x1 prime down to xn plus xn prime. And f of V plus W, f of f comma W, you take the coordinates of V plus V prime multiplied into the coordinates of W. You get x1 plus x1 prime y1 up to xn plus xn prime yn. Just distribute across, you have x1 y1 plus x1 prime y1. If you continue across, the last term you'll get here is plus xn yn plus xn prime yn. This is f of v plus v prime comma w. This is f of vw plus f of v prime w. This proves the first property of a bilinear form, and all the others are proved in exactly the same way. Why is it symmetric? Well, symmetric is easy. If v has coordinates x1 down to xn, and w has coordinates y1 down to yn, then f of v comma w is x1 y1 dot 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 up to xn yn. But these are just real numbers. In real numbers, multiplications is commutative. x1 y1 the same as y1 x1. So just reverse the order of all of these terms, and then you see this is exactly f of wv. So f of vw equals f of wv. So f is symmetric. And suppose we take f of the vector v with itself. That's going to be x1 x1 up to xn xn, which is x1 squared, the sum of the squares of the coordinates. And square is 0 or positive. This is going to be positive so long as v is not all, the coordinates are not all 0. Right? If you have the 0 vector, just 0 plus 0 plus 0. But any non-zero vector, one of these coordinates will be strictly positive, the rest are non-negative, so the sum is strictly positive. So f is positive definite. And a positive definite symmetric bilinear form is called an inner product. So a positive definite symmetric bilinear form on a real vector space, real means over the real numbers, is called an inner product. On the vector space. Recall the standard basis on the vector space V equal to Rn is the set of n vectors E1 up to E sub n, where E sub j is the vector where all the coordinates are 0 except 1, and the 1 is the jth coordinate. We usually denote the standard inner product by, we just write f comma w. And if you take the inner product of EI times EJ, where EI and EJ are the standard basis vectors, E1 is all zeros except a 1 in the ith place. EI has all zeros except a 1 in the ith place. EJ has all zeros except a 1 in the jth place. We take the inner product of these two vectors. If they're the same vector and you're adding sums of squares of coordinates, you get 0 plus 0, 1, and then zeros again. This is 1 if I equals j. But if the I and the j1s are in different positions, it's going to be 0. And this function, which is 1 if I equals j and 0 if I is different from j, is sometimes written delta ij, and this is called the Kronecker delta. So the Kronecker delta is this function of two variables, delta ij, which equals 1 if I equals j and 0 otherwise. And if you take the standard inner product applied to the standard basis for Rn, the inner product of two basis vectors, ei, ej, it's either 0 or 1. It's 0 if the vectors are different and 1 if the vectors are the same. So that's a nice observation. Now, it's important to note there are lots of inner product spaces in addition to the standard one. Let me take one that is familiar from calculus. Suppose we let V be the set of all functions f from the unit interval to R. So these are all continuous functions. And on the number line, this square bracket 0, 1, that's all the points from 0 to 1, including the endpoints. So this square bracket 0, 1, it's all real numbers t, such that t is between 0 and 1. And if we look at all continuous real valued functions, that's a vector space, which I'll write as C0, 1. This means C stands for continuous, and 0, 1 means the interval from 0 to 1. And if f1 of t, f2 of t are continuous functions on 0 to 1, then f1 plus f2, we define the sum of these functions to be f1 of t plus f2 of t. And this is also continuous. And f1 plus f2 is another function from 0 to 1. Also, if you take a function f and multiply it by a scalar c, you define the function cf of t to be just c times f of t. So with this standard definition of addition of functions and multiplication of functions by a number, this is a vector space. So C0, 1 is a vector space. Let's define fg, f and g are two functions, to be the integral from 0 to 1 of f of t, g of t, dt. So if f and g are continuous, so is their product. You can integrate a continuous function. This is some real number. And you can check the properties of the integral, say this is a bilinear form, and ff, the inner product of the function with itself, that's 0 to 1 f squared of t dt. This is just multiplying f by itself. This is positive unless f of t equals 0 for all t. If for any t, f of t is different from 0, the square is strictly positive, it's continuous, and the integral will be positive. So integration from 0 to 1 is an inner product on the real vector space of continuous functions from 0 to 1. So this is just a nice example to make it clear that the inner product of vectors in Rn is not the only inner product. When we have an inner product on a vector space, we can do some geometry and we can define the length of a vector. The length of a vector v in a real inner product space is denoted V with these square bars around it. And this is, you take the inner product of V with itself and take the square root. Now, let's just check this is consistent with what we usually think of as length. So suppose we're in R2, and here's the vector xy. So this is x and this is y. Let's call this V. So the length of V is the square root of the inner product of V with itself. The inner product of the vector xy with itself is x squared plus y squared. That's exactly the length of this hypotenuse, which is the distance from the origin to the vector. That's exactly the length. So this definition of length coincides exactly with what we think of as lengths for vectors in the plane. And this vector has the following obvious property. You take the vector and multiply it by a scalar, that stretches the vector by an amount, the absolute value of C times V. So. A unit vector is a vector whose length is 1. So U is a unit vector if the length of U is 1. And if V is not the zero vector, oh, I should also say, the length of a vector V is 0 if and only if the inner product of V with itself is 0, if and only if V is the zero vector. So the only vector that has 0 length is the 0 vector. If V is different from 0, then the length of V is positive. Suppose we let U be the scalar 1 over the length of V times V. Then the length of U is the length of the scalar 1 over the length of V times V. That's equal to, you can take the scalar outside, 1 over the length of V. I don't need absolute value signs because this is positive. V is different from 0. Times the length of V, that's length of V over itself, that's 1. So if I take any vector V and I divide by its length, there it is, this is always a unit vector. So taking a non-zero vector, multiplying it by 1 over its length, always produces a unit vector. So for example, if we had this vector, multiplying it by its length, if this would be, this would be the unit vector, pointing in the same direction, but has length 1. Suppose we take the vector space C01, and what's a nice function in C01? Suppose I take f of t to be the sine of 2 pi t. So that's a nice function. What is the inner product of two functions is the integral from 0 to 1, f of t g of t dt. So what is the length of the sine of 2 pi t? The length squared is the inner product of sine pi t with itself. That's the integral from 0 to 1 of this function multiplied by itself, sine squared of pi t dt. If you do this integration, you get a half. So that's the square of the length. So the function sine of 2 pi t, this has function 1 over the square root of 2. And length 1 over the square root of 2. So in a real vector space, the linear operator p from the space to itself, a linear transformation from a space to itself is called the linear operator. Operator just means you're going from the space into itself. So a linear operator t is called orthogonal if it preserves length. That is, the length of the vector t of v is the same as the length of the vector v for all v in the vector space. And orthogonal transformations are very important certainly in physics and engineering in many applications. Okay. Now, the nicest basis for Rn is the standard basis. The standard basis, E, consisting of the vectors E1 up to In Rn, satisfies the following properties. First, the inner product of EI and EJ is 0 if I is different from J, and the length of each vector E sub I is equal to 1 for all I. In general, we say that vectors V and W, let me make them non-zero vectors so it's clear. Non-zero vectors V and W are orthogonal, which also means perpendicular, if the inner product of the two vectors is 0. And a very nice lemma, in the notes, this is lemma 5.2. Every orthogonal set of vectors is linearly independent. So proof that S be a set of orthogonal vectors, and let V1 up to V sub k be a subset of S. I want to show these vectors are linearly independent. So that C1 up to CK be scalars such that C1 V1 plus C2 V2 plus CK VK is the zero vector. I want to show that all the scalars are zero. Must show C sub I equals zero for all I. How do we prove this? Well, suppose I take the inner product, C1 V1 up to C sub I V sub I up to C sub n C sub k V sub k, and I take the inner product with the vector Ci. Because this is an inner product, it's bilinear. The inner product with the vector Vi. So this is C1 V1 inner product with Vi, Ci Vi inner product with Vi, up to CK VK inner product with Vi. And I can take the Ci outside. This is Ci V1 Vi. I get a Ci Vi Vi up to CK VK Vi. Now, because these vectors are orthogonal, the inner product of any two of them is zero. So except for this term, all the other terms are zero. So this is equal to Ci, and the inner product of Vi with itself, that's the length of Vi squared, that's zero. But we're told these are non-zero vectors. Right? Every orthogonal set of non-zero vectors. So the length of Vi is positive, it's not zero. So C sub I has to equal zero. If this times this is zero and the right-hand term is non-zero, then the left term has to be zero for all I, which means these vectors are linearly independent. So orthogonal vectors are automatically a linearly independent set. A set of vectors is orthonormal if it is, first of all, orthogonal, and second, the length of V is 1 for every V in the set S. So an orthonormal set of vectors, the ortho means the vectors are mutually orthogonal, and the normal means each vector has length 1. So the standard basis, E1 up to En, for Rn, is an orthonormal basis. Every vector has length 1, and they're mutually orthogonal or mutually perpendicular. And an orthonormal basis for a vector space is very nice. And we'd like to find one. So we use the following very simple fact, or it's geometrically very important. Suppose I have a vector W and a vector V. So I would like to write V as a sum of two vectors. One is perpendicular to W, and the other is parallel to W. So this is what we would like. This is just in general. So fix a vector W not zero, let V be a non-zero vector. We want to write V as a sum of two vectors such that V1 is perpendicular, which means orthogonal, to W, and V2 is parallel to W. Parallel means V2 is some constant times W. Right? So here, this vector could be V1, and this vector would be V2, and V1 is perpendicular to W and V2 is parallel. And we can use the inner product to compute V1 and V2. So actually, I want V1 to be parallel and V2 to be perpendicular. So V2 will be the perpendicular one and V1 will be the parallel. So I make this definition, let V1 be equal to a certain scalar multiple of W. So W is a vector. If I multiply it by a scalar, that vector is parallel to W. So V1 is going to be, I take the inner product of V and W, and I divide it by the length of W squared. So this vector, so W is non-zero, so this denominator is non-zero. Whatever it is, V1 is definitely parallel to W. And I want V2 to be a vector such that when I add it to V1, I get V. So the easiest thing to do is to say let VD, V2 be V minus V1. Right? And I must show that V2 is perpendicular to W, which means I have to show the inner product of V2 with W is zero. So let me do the calculation. What is the inner product of V2 and W? So V2 is V minus V1, inner product with W. That's the inner product of V and W minus the inner product of V1 and W. That's the inner product of V and W minus, and what is V1? V1 is this. V1 is the inner product of V and W divided by the length of W squared. W, inner product with W. V1, this is V1 inner product with W. What is this? This is the inner product of V and W minus, this is just a scalar. I can take it outside. So that's the inner product of V and W over the length of W squared times the inner product of W with itself. But the inner product of W with itself is just the length of W squared. That's the definition of the length. So these cancel. And I get VW minus VW, and that's zero. So therefore, VW inner product with V2 inner product with W is zero. So V2 is orthogonal to W. V1 is parallel, V2 is perpendicular. That's my decomposition of V into a piece parallel and another piece perpendicular to W. And that's very nice. In fact, it's not hard to show that if you decompose V into a component parallel to W and a component perpendicular to W, those components are uniquely determined. So we have W and V, this component, this vector, this is what I call V1, is sometimes we write this the component of V in the direction of W. And this is the orthogonal component. Let's actually work out an example. Suppose I let V be the vector 3, 2, and W be the vector 7, 3. Let's see. Let me try and draw a picture of this. So the vector 7, 3 is 2, 4, 6, 7. This is 3. That's W equal to 7, 3. The vector 3, 2 is there. That's V equal 3, 2. So the component of V in the direction of W is the inner product of V and W divided by the length of W squared times W. The inner product of these two vectors, you multiply coordinates and add. 7 times 3 is 21. 2 times 3 is 6. 21 plus 6 is 27. The length of the vector 7, 3, 7 squared is 7 squared plus 3 squared. 49 plus 9 is 58. So times the vector W. So this is the vector. Let's see. 7 times 27, this is 189 over 58. 3 times 27 is 81 over 58. So this is the component of V parallel to W. That's my V1. I want to write V as a piece parallel to W and the piece perpendicular. This is V1. This is V2. So this is what V1 is equal to. And V2 is W minus V1. W is 7, 3 minus 189 over 58, 81 over 58. So if I put this over a common denominator of 58, sorry, V2 is V minus V1. Then I want V2 and V1 to add up to W. So V is 3, 2 minus that. Let's see. 3 minus 189 over 58, that's 150, 174 That's minus 15 over 58. And 2 times 58 is 116 minus 8 is, oh, sorry, this is 81. So 2 times 58, 118 minus 81. No, 2 times 58, 116 minus 81 is 35 over 58. That's V1, that's V2, and that's what they look like. Okay, now, what is very important, certainly historically in linear algebra, is a solution to the following problem. Given a basis for a vector space V, finite dimensional, construct an orthonormal basis for V. So an orthonormal basis is a basis of unit vectors that are mutually orthogonal or perpendicular, and it still is a basis. And you want it actually to have the nicer property that if the basis is, W1 up to WK, your new basis, say V1 up to VK, V1 up to VI will generate the same source space as W1 up to WI for the original basis. And there is a solution to this problem, which is called the Gram-Schmidt orthonormalization process, or algorithm. Of course, it really is an algorithm to solve the problem. So the last thing I want to do in this talk is describe the Gram-Schmidt process. So in the notes, I've broken this up into a couple of steps. Let's see how we're going to do this. So in Gram-Schmidt, I can start with the following observation. If V1 up to Vn is an orthogonal basis for a vector space W, vector space V. So that means that if I take the inner product of Vi and Vj, that's 0 for all I different from j. That just means every two different vectors are mutually orthogonal or perpendicular. Then if I let Wi be Vi divided by the length of Vi, any vector in the basis is non-zero. This is a unit vector. And maybe I'll call it Ui. And U1 up to Un is an orthonormal basis for the vector space, right? If these vectors are mutually perpendicular and I multiply them by scalars, I stretch them, but I don't change their direction. They're still perpendicular. And if I multiply by a scalar that makes them a unit vector, then each of them is a unit vector. And that's the definition of orthonormal. An orthonormal set is a set of unit vectors that are mutually perpendicular. So to carry out the Gram-Schmidt process, it's enough to construct an orthogonal basis. And then the last step would be to divide each vector in that basis by its length, and you get an orthonormal basis. So the idea is really very simple. Suppose that W1 up to Wn is a basis for a vector space V. Let V1 be equal to W1. That's fine. What do we do with V2? So we want to compute a vector V2 parallel to W2 and perpendicular to V1. But we know exactly how to do that. Here's the picture. Here's the vector V1 equal W1. Here's the vector W2. We want to find a vector parallel to W2. Sorry, that's not what I want to say. Let me say this properly. I want to compute a vector V2 that's perpendicular to W1 such that V1 and V2 are linearly independent. So I know, given W2, I can find a vector. I can write W2 as a vector parallel to V1 and perpendicular to V1. So let V2 be the component of W2 perpendicular or orthogonal, same thing, V1. And we found the formula for that already. So I can write W2 as a piece parallel to V1 and a piece perpendicular to V1. So I can write W2 as the inner product of W2 and W1, or in V1, divided by the length of V1 squared times V1. That's the component of W2, well, I call that prime, parallel to V1, and let V2 be equal to W2 minus this. That's exactly what we defined as the component of W2, or construct as the component of W2 perpendicular to V1. So V2 and V1 are perpendicular. Their inner product is 0. That's how we constructed this. And anything that's a linear product of W1 and W2, which means V1 and W2, will be a linear product of V1 and V2. So the subspace spanned by V1 and V2 is the same as the subspace spanned by W1 and W2. So this gives us a second vector. And suppose we've done this k times. So that V1 up to V sub k be mutually orthogonal, an orthogonal set. That means every pair of vectors in that set has inner product 0, every pair of different vectors. And suppose WK, V1 up to VK, that set, VK plus 1, WK plus 1, is linearly independent. So we want to construct VK plus 1 such that VK plus 1 is perpendicular to VI for all I from 1 up to N, and the subspace generated by V1 up to VK and VK plus 1 is the same as the subspace generated by W1 up to WK and WK plus 1. So let's construct or compute the sum. I goes from 1 up to K. Each of these VIs intersected with WK, each of the VI's inner product with WK plus 1 divided by the length of VI squared times VI. And let, sorry, this is W, yeah. And let V sub K plus 1 be equal to WK plus 1 minus this. So I'm sort of extending the construction from one vector to K vectors. Compute the inner product of VK plus 1 with one of these VJs. So that's WK plus 1 inner product with VJ minus the sum, I goes from 1 up to K, VI WK plus 1, that inner product, over VI squared, VI VJ. But the VIs and the VJs are mutually orthogonal. So all these inner products, this is 0 unless I equals J. And when I equals J, this is just the length of VI squared. So we get WK plus 1 VJ minus, all these are 0 except when I equals J. When I equals J, this is VJ. By the symmetry, WK plus 1 VJ over the length of VJ squared times the length of VJ squared. These cancel, then this cancels, and we get 0. So all these vectors are mutually perpendicular, and if something is a linear combination of V1 up to VK and W sub K plus 1, it's a linear combination of V1 up to VK and VK plus 1. So this construction really does everything that we want. Now, it's hard to figure out what it is I just did just watching this in the lecture. And if you read the notes, you'll see this in the section on inner product spaces, where I think it's pretty clear. And let me end by just doing an example. So, example. Example, Gram-Schmidt. So in R3, consider the vectors V1 equal to 0, 1, 1, V2 equal 1, 0, 1. V3 equal 1, 1, 0. So the set V1, V2, V3 is a basis for R3, but it's not orthogonal. Right. For example, if you take the inner product of V1 and V2, that's 0 times 1 plus 1 times 0 plus 1 times 1. That's equal to 1. It's not 0. Right? And so on. Also, the length of V1 is the square root of 1 squared plus 1 squared. That's the square root of 2, which is not 1. So these vectors do not have length 1, and they're not mutually perpendicular. So I want to apply Graham-Schmidt to get an orthonormal basis. So let me start with, here I have V1. So let W1 equal V1. And W2 is going to be V2 minus the inner product of V1 and V2 divided by the length of V1 squared times V1. Or I can do this with W1, the same thing, W1 squared. What is this equal to? V2 is 1, 0, 1. The inner product of W1 and V2, this inner product, is 1 over the length of V1 squared, which is 2, times W1, 0, 1, 1. So this is a half. So this is 1, 0, 1 minus 0, a half, which is 1 minus a half. So that's my vector W2. How do I get my vector W3? W3 is going to be V3 minus the inner product of V3 and W1 divided by the length of W1 squared times W1 minus the inner product of V3 and W2 divided by the length of W2 squared times W2. So let me do this calculation. V3 is 1, 1, 0. The inner product of V3 and W1. V3 and W1, that inner product is 1 over the length of W1 squared is 2 minus a half times W1 minus the inner product of V3 and W2. This is W2. If I take the inner product of this with the vector 1, 1, 0, that's 1 minus a half. That's a half over the length of W2 squared. The length of W2 squared is 1 plus a fourth plus a fourth. That's 3 halves times W2. So that's equal to 1, 1, 0 minus 0, a half, 1 half over 3 halves is 1/3 minus a third, minus a sixth, minus a sixth. So this is 1 minus a third, 2/3, 1 plus a sixth, no, 1 minus a half plus a sixth is 2/3, minus a half plus a sixth is minus a third. No, minus a half, oh, this is plus, minus 2/3. So W1 is V1, W2 is this, W3 is this. Suppose I normalized, get the unit vectors. So the corresponding unit vectors, I let U1 be V1 divided by the length of V1. The length of V1 is the square root of 2. So this is 0, 1 over root 2, 1 over root 2. U2 will be the length of W2 divided into the vector. This has length 1 plus a 4 plus a 4, 3/2, square root of 3/2. So if I multiply this by the square root of 2/3, I get 2 over root 6 minus 1 over root 6 minus 1 over root 6. That's a unit vector. And U3, that's this vector. The length of this vector is 12/9, 4/9, 4/9, 4/9, 12/9 times 3 is 12/3. This vector has length 4. Two. So the length of this vector, 4/9 plus 4/9 plus 4/9 is 12/9. Square root of that is 2 root 2 over 3. So 3 over 2 root 2 is 1 over root 2. So if I do the arithmetic correctly, I get U3 is 1 over root 3, 1 over root 2 minus 1 over root 3. And this is all done neatly in the book on 284, 285. So this is Gram-Schmidt orthonormalization, and it's a useful bit of beginning linear algebra. And that's it.